Okay, welcome back from break. We are at the section of this class today where we're going to do some lecturing. But before I do that, I want to say that what I'd like for you to take away from that last piece that we just did is the idea that you now have several pieces, several templates that you can use when you're writing about regression from lots of different fields and lots of different areas. So if you have to write up an F-test or an R squared, then you're able to pull up this document and look and see how published papers, how they have done an R squared, and hopefully use that to help inform you of what an R squared tells you and how that R squared works. Okay, so that's what that's there for. And now let's talk a little bit more about interactions. I did see that several of you said that you were feeling uncomfortable with the idea of interactions, and that's totally normal. You will notice on the schedule, I have 3 weeks to teach interactions. And then there's really a 4th week where we still keep teaching interactions. So we are at the very early stages. There's a reason that you're not doing an interaction for homework this week. It's because you're still learning about how they work. So don't be too afraid of them yet. We're still going. So the basics of an interaction model are that they allow the strength of the relations between one x variable and the outcome, or y, to vary across levels of x2. Now, the idea behind an interaction is that it's theoretically motivated. Just like it was with hierarchical regression, you need to have a reason to think that this might exist. And so it starts with the research questions that you're asking. So with my blue light blockers question that you all did some discussion board posts on, which were very fun to read, everyone has excellent graphing skills. I was very impressed with the graphs I was able to see. You'll have to teach me because I don't know. All mine are in Excel. So is that for blue light blocking glasses, we're looking at the relationship between amount of screen time and amount of sleep you get across levels of whether you wear a blue light blocker. So that's my X2. So here is my going through looking at how these might have played out. Most of you graphed something that looked like this, where we have the lines were not parallel. You are all believers in blue light blocking glasses. And so and with the idea that they are differentially helpful, that if you're in a control situation where you're not wearing blue light blockers, that the more screen time you have, the less sleep you're getting. That relationship for most of you is still negative. The more screen time you have, the less sleep you're getting, but it was less negative when you're wearing those blue light blockers. This was my example of if you think blue light blockers are a little bit effective, but not really, and they're not differentially effective, there's no interaction here. There's a little bit of a difference between my estimated amount of sleep based on whether you had blue light blockers or not. But those lines are parallel, so there's no interaction. They're not differentially helpful. They don't help more with more screen time. So an interaction is a test of whether these lines are going to be parallel, essentially. So within within an interaction model, the interaction coefficient is testing basically whether the relation between x1 and y is different across levels of x2. Or in simpler terms, it's testing whether the lines representing the relation of x1 with y at 2 values of x2 are parallel. If the interaction term that you've put into this regression model is significantly different from 0, it means the lines are not parallel. There is a differential relation. But if it's not significant, it means those lines are parallel. So in an interaction model, you're testing to see whether it's differentially related. Now, technically, how we've been interpreting all of these coefficients before is A 1 unit change in x1 holding x2 constant is associated with this much change in y. Now, technically, you can actually do exactly the same thing with the interaction. It's just a little bit head spinny. Before I say this out loud, know that you never actually have to interpret it this way. Really, what you're trying to look at is, does the relationship of x1 with y depend on x2? That's what you really want to know. But what this number means, it's the amount that the slope of b1 on y changes when b2 changes by 1 unit. So if you think about it, come back here. This is the relationship of b1. This is the relationship of b1 with y when b2 is equal to 0. And as I move it up by 1 unit, I move it to with blue light blockers. And now I'm talking about the slope of this line. So the coefficient of the interaction is the difference between this slope and this slope. Sometimes interactions, when you're presented in a paper, they're called moderators. Did anybody have interactions in their model? I think I saw several. Did they maybe call them moderation, or was it all about interaction? Yes, I see at least 1 or 2 people saying yes, they called them moderators. So have a look through the document. You can find those. In an interaction or a moderation model, sometimes they conceptualize it as one variable is moderating the relationship of another variable with y. That's the same thing as the relationship of x1 with y is dependent on x2. But this might be easier to understand. This might jive with your brain better. So I like to put both conceptual explanations up front. So a moderator variable is a third variable that would affect the correlation between 2 other variables, an x1 and a y. Or you can think about it as a variable that affects the direction or the strength of the relation between a predictor and an outcome. And all of these are just different ways to say x1 and y is dependent on x2. So any interaction model that you see is also a moderation model. They're the same thing. They're just called different names sometimes. So any interaction that you run could also be phrased as a moderation. So I rephrased our blue light blocking interaction questions as moderation questions. Does using a blue light blocker moderate the relation between screen time and hours of sleep? If it moderates it, then our lines representing the relation between screen time and hours of sleep are going to be different across the different levels of blue light blockers. Here's another way you can say it. Does the relation between screen time and sleep depend on whether the participant is using blue light blockers? Those are both moderation style interaction questions. So you can use these as you think about potentially phrasing your own questions. In a couple of weeks, we have your very first interaction. Will be not this coming week, but next week you'll do your first interaction, and then you have your actual homework, your final project draft will come in. Can't believe it's already halfway through the semester. So you might want to use a moderation. You are not required to for your final project, but if you do, these are ways to think about your questions. So how do you test whether the lines are parallel? How do you test whether the blue light blockers are effective or differentially effective? You do it with math. So interaction models are called non-additive models sometimes in textbooks when you read them, because we're no longer just adding coefficients together. Now we're going to multiply them by each other. Interactions are product variables. Do you remember product? It's like multiply one thing times another thing, and the result is the product. So here is an equation that contains an interaction. Here I have y equals b0 plus b1 times x1 plus b2 times x2, all of which you're familiar with. But then we have this new thing here, which is B12 times X12. And this is how we represent the interaction. And we represent it like that because X12 is literally the product of the first two X's. And that's not like a figuratively, literally. It's actually literally. You multiply one by the other. You make it by literally multiplying X1 times X2. And I'll show you what that looks like. This is the car sales data set. Each row is a different car make and model. There I have Acura Integra, Audi A6. Again, this is a very old data set. We've used it before in this class. It comes with SPSS, so if you have SPSS on your computer, this data set is on your computer somewhere. Okay, so first, before we get to the interaction model, I'm going to show you an additive model with these data because it's a multiple regression model, something that you're used to. So in that car sales data set, I have the rows that are make and models. My outcome variable is going to be resale value. So the price of the vehicle after it's been on the road for 4 years. And then my predictor I'm going to put in this model is truck, whether the vehicle is a truck. 1 is yes, it's a truck. 0 is no, it's a car. And my other predictor is sales, which is the number of cars that were sold in thousands of cars. So a 1 unit increase in sales is 1,000 more sales. Okay, so my research question in this with these two predictors, resale value and resale value being predicted from truck and sales, is for any two vehicles with the same type, do vehicles that sell more have a higher resale value? Does that make sense? What do we think? Economics-wise, which would be more likely? If I have one car that sold 100,000 units and one car that sold 5 units, which one's probably going to sell for more?
Cars or trucks?
Ah, good point. I don't know. Cars?
5.
5, maybe?
The 5, yeah.
Yeah, but per economics, like supply demand, it should be the opposite. Although I guess you could argue the other way around, which is if it's really popular before, maybe it's gonna keep being popular later. Maybe, I don't know. Let's find out.
I mean, also, if there's only 5 of them and people want to collect them or something, then, well, I mean, like, they can sell for higher.
True. If you've got, 5 Batmobiles in the world, they're probably outliers in this data set. Gotta catch them all. They're Pokemon. Okay, let's see what we've got. So what I have here are the results from a standard multiple regression. Oh, thank you, Jamie. It's called the scarcity principle. It actually has a name. All right, so from our standard multiple regression, which is both of those predictors, our dependent variable here is resale value. And our predictors are, is the vehicle a truck versus a car, and sales in thousands. And so this is not differently interpreted than any other regression we've done so far. This is telling us that on average, we are doing a good job of predicting the error in this model compared to a grand mean model. And we're explaining about 7-8% of the variance. Here are the results of the additive model. We can harvest these numbers to create an equation. So our intercept is 20, sales is 0.43, sorry, and whether the vehicle is a truck is negative 3.54. So the next thing I have in here is we can actually take these and harvest them and make a graph in Excel. We can do that using reasonable values of x1 and x2, and we can plug them into the equation. The reasonable values for the x's for trucks is 0 or 1, 0 being cars, 1 being trucks. And reasonable values for x's are sales in thousands. And if I look at the SPSS file, the minimum there was 0 and the max was 540. The mean was 53,000. Well, that's kind of dumb. We have 0 sales. Why are we even predicting that? Oh well. All right, so from Excel, I'll show you what this Excel document looks like. What I have here is the equation that I harvested from that output table. I've taken each of these 3 components and I put them in their own cell. Here it is for constant, 20, and for sales, and for truck, 354. And then I used those to do the math for 4 values of sales. So each one of these is an equation. I'll show you how this works in a second when I pull up the Excel spreadsheet. And it lets me get a expected score, an expected amount of resale value for each of these probable values of X, of both my X's. So I get them for cars and I get them for trucks. Big whoop, it's straight lines, whatever. It matters because here in a second, we're going to do it for interactions. So you can see how it's different. Okay, so our old question that we just answered was, for any 2 vehicles of the same type, car or truck, do vehicles that sell more have higher resale value? Wait, what was the answer? No. Vehicles that sell more do not have a higher resale value. In fact, they have a lower resale value. Scarcity principle wins. We are not in economics 101, or we probably would have guessed that as our hypothesis. And who sells more holding sales constant? Who's got better resale value, cars or trucks?
The cars or the not trucks?
The not trucks. Shantanu has it, but spoke up first. Oh my goodness, look at this terrible typo here. I have been presenting on these slides for years, and I think I have never noticed that typo. What does that even say? Vehicle? Shame. Finger wagging at self. All right, so trucks don't sell more or don't have a better resale value. Cars do because they, this coefficient is negative. So as the coefficient of truck goes from 0 to 1, the value goes down. I'm pointing at it. That doesn't help. Okay. So now here is our new question. This is our question that includes the interaction in the model. Is the relation between sales and resale value dependent on whether the vehicle is a car or a truck? Or I could say, is the relation between sales and resale value moderated by whether the vehicle is a car or a truck? So here's my new equation. Resale value is sales, a truck, and then sales times truck. That's the new thing that we haven't done yet. So in order to do this, this is what you'll learn with Susan this week. You'll learn how to create these new variables. So you have to create a new variable for this equation. This variable is called sales times truck. Although I did just get the brand new version of SPSS this week. Maybe they finally added the ability to do interactions, but up until now, you've had to physically create any interaction variable you want. So we'll see. You create it by multiplying them together, which is literally, do I have the, can you see this here? Truck times sales. Okay, so if I back up here, sorry, everybody close your eyes. Okay, here I have sales. This is the sales column. Right next to it is a column called trucks, and it's either 0 or 1. So if I multiply sales times trucks, half of those values are going to be zeros, and the other half of them are going to be the same. They're going to be 1. So that new interaction value is 0 for half of them, and it's equal to this for the other half, depending on which car it is, whether it's a car or a truck. Okay, so now close your eyes again. I'm going to get back to where I was. Okay, so now what happens next is that variable gets entered into a regression. Just like before, we have sales and truck and the interaction term. The interaction output the output from the interactive model is actually identical to what you've seen before, because as far as SPSS knows, this is just a regular old regression. The data and your stats package, they do not know where they come from. You are the only one who knows. And so, as far as it knows, you just put in another regular old variable into that model. You are the one who has to know that it's different. So these are actually interpreted exactly as you did before. Here's your R squared. I'm explaining more variance. I think before it was like 8%, and now I'm at like 14% of the model. And my f-test is significant, so overall I'm doing a good job. Each of these variables is doing a good job. So now in this coefficients box, where we're used to spending most of our time, we're going to spend most of our time here today. We have the constant, we have sales, we have whether the vehicle is a truck, and we have the new variable we created. And so this constant we interpret as when all the other ones are 0, because remember what our equation looks like. We just now have a new term in it, b12 times x12. So we have to think about when all of those are 0. And so it is the average resale value for cars, because that's when truck is 0, who sold 0,000 units. That's our resale value, $22,000. Okay. Because when both of those are 0, the interaction term is also 0. Because it's multiplying. So now here, for sales in thousands, remember how before with your constant, you always had to interpret it at 0? And in your regular interaction model, you had to say that to interpret one of these values, you had to keep the others constant. So now with an interaction in the model, you have to ramp up your specificity. And so here, what we'll say is that for cars, because that's holding this at 0. So you can't just hold it constant. It has to be when it's 0. When all the other predictors are 0, sales in thousands, an additional 1,000 sales is related to a lower resale value. So what I've done here is I can't say holding vehicle constant. It has to be just for cars, because I have an interaction term in the model. And I'll show you why in a second. And we do the same thing with the other coefficient, which is when sales are 0. So for any 2 cars with 0 sales, trucks have a lower resale value, which is $5,000 less, but it's not significantly different from 0. You could also say for any 2 vehicles that had 0 sales, there is no difference in the resale value for trucks and cars. Okay, so that's how you interpret that. So far, all we've done to change up what you've done before is you can't say holding constant, you have to say at this point. Again, I'll show you why in a second on graphs. Now the interaction, this is your new guy. This one is saying that it's asking the question of whether the relationship between sales and your resale value is dependent on whether the vehicle is a truck. And so I'm testing the significance of that. And because this is significant, it's telling me that there is a differential relationship. So it says the relation between sales and resale value is dependent on whether the vehicle is a truck. That's our interaction. This tells us that the lines representing the relation between sales and resale will be dependent on whether the vehicle is a truck. So if you have a separate line for a car and a separate line for trucks, they will not be parallel. In what way, you might say? How? Well, let's go to Excel and I'll show you. We will graph it. Hello. Hopefully, I'm still screen sharing. Come here. No, don't look. Hope you didn't see it. Okay, what I have done is I've harvested that equation here. My constant was 22.8. Uh-oh, on slide 13, truck was equal to 1, and on slide 22, truck was equal to 0. Well, let me check. Truck should always, it should always be the same. Car should always be 0. On slide 13. Oh, I think I added a slide. Uh-oh. Yes, truck is 1. Truck is always 1. Is the vehicle a truck? 1 is yes. Oh, no. Yes. No. Okay, hold on. That's not oh, no. This is correct because the average resale value for cars is, it's because it's cars when truck is equal to 0. So when truck equals 0, we are talking about cars. Does that make sense? Okay, great. Thank you very much. Now let's go back to Excel. Okay, so I've harvested each of these from that Excel document. First, I'm going to show you how I did this one because this one was the easier one. So, hello. Oh my goodness. Hang on. It's just like have this mind of its own here. There we go. Okay, so here's the graph I showed you. And here's the equation that I harvested. Here are those 3 coefficients. And here are my probable values. I have car when this is 0. When it's 1, then we're talking about trucks. For sales, I have these 4 probable values of sales. And here is my equation. If you haven't used equations in Excel, they're extremely handy. So what I've done here is I've said, I'm going to take this one, 20. I'm going to just erase it, and then I'll do it again. So it's equal to this one, which is 20. And if you push the F4 button, it makes it so it never moves, no matter what you do with copying and pasting. So that's real handy. So that one, because that's here, 20. And then I'm going to say plus, because I'm adding the next term. Oh my goodness. Plus 0.43 times sales. So here's that one. Negative 0.43. Again, I'm going to use the F4 button. Times my value for sales that I want to plug in here. That's where on my x-axis, which is right here, 3. Okay. And then I'm going to say plus again. And then the next one here is truck. So this value here, 0.354. Use that F4 again. And I'm going to say times this value, because that's my value for when it's a car. So that's what's going to go here. You can cycle through your values, but I can't remember how they work. So once I've done that, this is the result of that equation. So I have 20 as my expected score here. And then if you look right here, it's a little bit different. I can actually tell you how different it is. .354 different. Do you know why? Where's that number?
Next to B2?
Yeah, next to B2. Exactly, because I've gone from here to here. And that's increased B2 by 1 unit. As I increase B2 by 1 unit, the difference is always 0.354. That's the difference between each of these variables here. Okay. Now, if I did the other way around, so here, let me just to illustrate how this 1 unit thing works. 4, 5, 6. Those are all values you could have. But the difference between 3 and 4 with holding one constant, so I'm holding this one constant because I'm looking at 2 cars that differ by 1 unit on sales. They're going to be different by 0.43, which is the same as B1. And that will be the same, copy, paste, 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 not there. It'll be the same across all of these. Anytime you increase by 1 unit. Now, if I increase by 10 units,
0.43.
33, you have to multiply it. 3 to 33, I've gone up by, that's not 10 units. What am I talking about? 13. If I go up by 100 units, did I do that math wrong too? Oh my God. 13. 3 plus 100 is 103, right?
Mm-hmm.
What did I do wrong? Oh. I'm subtracting the wrong things.
Oh,
There we go. There. So now I've gone up by 100 units.
yes.
4.3. So you can play
What-
around with these to sort of see what would happen. This is not accurate anymore. Oh my
So,
God.
Dr. Logan,
Yeah.
those, the 3, the 13, and the 103, can we use those to mark our x-axis? I mean, our y-axis as well. Is that fine? Like if I did 3, 4, 5, 6, and I just used those 4 and did a graph with those 4, I can just mark the y-axis with those instead.
So yes, but traditionally we think of an x-axis, because you're talking about actually marking the x-axis. You would want to mark it with evenly spaced bits.
Right.
And so you wouldn't want to do 3, 13, and 103 because they're so far apart. Now you could do 3, 103, and 200.
Or, yeah, got it. Yeah, understood. Whatever is like, yeah.
Right,
Yeah.
you could do it like that, and now you have something that is a straight line. You could pick quartiles. Yes, you could pick, as long as you're picking things that are evenly spaced, it makes sense. So now what I want to show you is how this changes when we do the interaction model. Now here I've picked 4 points, but for Excel, you don't actually need 4 points, for X values. You really only need 2 points to determine a line. Remember that? That's from geometry that I failed in high school. Look at me now, Mr. Lane, in your face. All right, you need 2 points. He used to say 2 points to determine a line. We need 2 points. All right, so let's make this equation. I've harvested each of these pieces, 22.09, 0.5, 5.6, and 0.081. All right, so all I'm going to do is recreate this equation using Excel math, and I wish I could make this bigger. But as I type here, you should be able to see most of it. Okay, so I don't have to type the y because that's the result of the equation. I'm just going to type equals. My first thing is this guy, 22. And I just use the F4 button to put the dollar signs in front of it. Plus this one, which is my B1, times this is my probable value for B1 that I'm interested in using here. That's a low value, no sales. Plus, what's next? The one for truck, So that's B2. Again, I'm going to use the F4 button just so that when I copy this in a minute, it doesn't mess me up. And then I'm going to take this value that I have here for trucks. Plus, sorry, everyone. Hold on. I glitched out here. This one times this value for trucks. This one got lost too. Times this value for... Hold on. We got lost. I'm going to start over. Intercept plus this one times whatever B1 is, which is sales. This is my sales value that I've plugged in, plus my B2 value times my B2. Now, do you remember how we make the interaction term?
We multiply the variables.
Multiply, multiply. So I'm going to say this one times this one times this one. Now I have all the pieces. So that's my expected score when my first sales were 0 for a truck. And now I'm going to copy it over here and then fix the formula so that I'm still talking about this one. This is my expected score. Why do I keep saying score? My expected resale, 4-year resale, when cars are 0 and original sales are 0. Now, let's do it for a higher sale value. What's the difference? Let's look at the difference. Remember how we did this? Which one makes sense? We're going to do 1 minus 0, negative 5.691. Do you see it? Right here. No. Give me a color. There we go. There they match. That's the difference. Now here, as I move this down, excuse me, I have to take this because I didn't use the fancy modeling here. All right, so now here is the expected resale value for trucks that sold 200,000 units at first. And I could do the same thing here. Don't worry, it's not actually 245. Oh my goodness. So it's way smaller. All of those numbers are correct. Now let's look at the difference here. Look at that difference. That number is not anywhere over here. And I don't think it's because I screwed up. I'll show you why. It's because of our old friend centering. So let's look at, here's the resulting guy here. Let me harvest all of these horizontal axis. All right, here we have a separate line for trucks and a separate line for cars. Let's look at the slope. Look at our different slopes. Do you see that the relation between the difference between trucks and cars is dependent on where we put our guess. So if I have, let's do 1 unit. If I only have this, that's going from 0 to 1,000 units sold. 0 to 100 units sold. That's maybe better. Ugh, I can't decide. Hold on. What did I have here first? 200. Okay. So depending on where our center is, the relationship or the difference between cars and trucks is going to be different. So what was our B1? Our B1 is sales. Our B2 is truck. And this is sales times truck. So here, where our intercept is, when sales are 0, who sells more units, cars or trucks? You can look here too. Which, oh, that's terrible. I'm sorry. What's the higher resale value? I apologize.
Cars.
Yeah. Do you see how here the orange line for cars is higher? But if instead I was looking down here, when there's 200,000 units sold at first, who's got a better resale value? Cars or trucks?
Truck.
Now it's trucks. The other thing I have seen that I see here is the relationship between resale, original sale value or original number of sales and resale value is very close to 0 for trucks. But it's strongly negative for cars. More popular cars are not selling well. But it doesn't matter how popular the truck is, it's still selling just fine 4 years later. And then Hadley asked, is that because it doesn't make sense that there would be 0 original sales, but then have a resale value? Yeah, I think it might be. So reasonable, let's say we start at 5,000 original sales. That's a very rare vehicle. It doesn't move much. So if we start at 100, that graph might make more sense. So you can see how, I think, let's just for fun, let's look at negative 100. Look at the difference there. So if you, this goes back to that article you all read about the sprinting and extrapolation outside of where you're really examining. Now that sprinting article was an interactive model. It was a moderated model. They fit a different slope to males and females. Just like here, we're fitting a different slope to trucks and to cars. So we don't have anyone who sold 0 units, or let's say even 10,000. Maybe it's based on selling 10,000 units. I don't know. Even there, we're expecting there to be a difference favoring cars, whereas in the long run, it's not. So this is how these two ideas interact. So I will put this interaction thing on the whatever it's called, on the Carmen, or as everyone else says, canvas, on the canvas. Okay, other things about these graphs. I'm really showing you these graphs not because I need you to be able to make them tomorrow, but mostly because I think it's a good illustration of how these models work and how the math works that sort of underpins them. Okay, so now I'm going to need to do a vote because, oh no, I've got time. This is perfect. So the last thing I have is I wanted to do another example with you, and I'm going to do it with the CATS data set. If I can make it pull up. When you guys are open, it hides everything. All right, so I'm going to pull up the CATS data set. Remember this one? We have 52 personality traits about cats. And I'm going to walk through one more regression model with an interaction with you and show you the results. And then I have a quiz for you. So I'm going to make a new variable. One of the variables we have in here that we're going to use is we have Australia, like whether the cat is from Australia or whether the cat is from New Zealand. We also have whether the cat is male or whether the cat is female. So I would like to use one of those dichotomous variables. I'm going to say, let's do male. Is the cat male? And if anybody has anything they definitely want to pick, how about calm? Okay, I'm interested in shy, cooperative, active. Any of these sound interesting? Zoom classes. Somebody type something in here that you want me to put in this model. Eccentric. All right, what's going to predict whether a cat's eccentric? Whether they're cool and whether they're vocal. Let's see. Ooh, cooperative. Do we think one of these is more like, oh my gosh, suspicious. They're so funny, aren't they? All right, we have a vocal. So where's the vocal? 44. So we're going to predict how eccentric a cat is from how vocal they are and whether they're male. So what I have to do so first what I'm going to do is I'll run this regression model. So this has whether they're eccentric, and it's going to predict it from whether they're vocal and whether they're male. And my output is hiding over here. So we're explaining 2% of the variance. Whoops. And there is a difference in vocal and eccentric. So cats who are more vocal, two cats who are both male or both female, the more vocal cats are more likely to be rated as eccentric. That makes sense. So now we can add an interaction to the model. I'm going to call this new variable int male vocal so that we know what it is. And I'm going to make that be the multiplication of these two. So now I have this. Now my new variable is at the end of my data set. And you'll see that for some people who rated their cats, they have a score 6, 6, 5, 1. And for others, they're just 0. So you know that these ones that are 0, these are the female cats. Because female is 0 when male is 1. Okay, so that's what that looks like. So now I can take this regression model and I'm going to add this new variable that I just made to the end here. Personality, and then this interaction between the two. Okay, my R² has not improved. It is still 2%. And now as I move down, my F-test is still significant. What I see here is that for cats who are female, being more vocal is associated with eccentricity. cats who are female and have a 0 on the vocal scale are rated as a 2.7 on the eccentricity scale. And the relationship between vocality, how vocal a cat is, and how eccentric they are is not dependent on whether they are male. Because this is not significantly different from 0. In other words, these two lines would be parallel. Now, just for fun, let's see if people from, so gender does not moderate whether a vocal cat is more eccentric, whether the relationship between how vocal a cat is and how eccentric they are. It does not moderate that relationship. So just for fun, what I'd like to do is put in this variable, which represents whether the cat is from New Zealand or Australia. Come on. And I'm going to do that because it turns out that people from Australia and people from New Zealand have different ideas of what makes a cat like personality wise. So from this first one I ran here, this is how vocal they are and whether they're from New Zealand, predicting eccentricity. Oh my goodness, look at this. It is still the same, 0.017. Not changed at all. 2% of the variance. Again, how vocal a cat is related to how eccentric they are, but people from New Zealand, holding vocal constant, cats in New Zealand are not rated any differently than cats from Australia. Okay, and now to put in the interaction model. Uh-oh, I did something wrong. Oh, I didn't calculate the new variable first. So I just ran this, which will calculate my new variable, which is personality times whether they're from New Zealand. And you'll see it's right here. Something is not right because they're all zeros. Or maybe it's just sorted by whether they're from New Zealand. Indeed it was. You see all these? Now I got values. Up here, they're all 0. So these are the Australian cats. All right, now running this regression model, still nothing, 0.017. R squared, 2% of the model, 2% of the variance predicted. So here we have, for any 2 cats who are from Australia, the relationship between how vocal they are and how eccentric they are is positive and significant. Cats who are more vocal are also more eccentric. But holding vocal, for 2 cats who are 0 on vocal, the difference between a cat from New Zealand and a cat from Australia is 0. There is no difference. And being from New Zealand does not moderate the relationship between how vocal a cat is and how eccentric they are. Okay, that was a lot of words. So what I want to do with our last like 10 or 15 minutes is I have a quiz for you on Carmen. And let me show you what the quiz is about. The quiz is using the same data set, and we're going to look at how playful cats are. That's my dependent variable, my outcome. And we're going to predict it from how curious they are, and this variable that represents whether they're from New Zealand or Australia, along with the interaction between the two. This says CURNZ, curious times New Zealand. That's what that represents. And you will use that to answer all of the questions. And what I'm going to do is I'm going to stop this recording, and I'm going to give you about 6 minutes to work by yourselves, and then I'm going to put you into breakout rooms to discuss the answers to the quiz.